Hello everyone, in today's class we're going to look at Bernoulli's principle, which is one of the main topics in fluid mechanics. So what is Bernoulli's equation or Bernoulli's principle? Well, it's a rule in fluid dynamics that explains how the velocity, pressure, and height of a moving fluid are related. So generally, when the pressure of a fluid increases, the velocity decreases. And when the velocity increases, the pressure decreases. And some practical examples are a plane, for example, a plane wing. As the wind accelerates and moves faster, the velocity increases. What would end up happening is that the pressure decreases, causing a lift for the plane, and that's how planes fly. Another example is if you have two sheets of paper and you line them up next to each other and you leave a small space in between, or a large space in between, and you blow high speed air in between with a velocity. It's a high velocity, the velocity increases. What ends up happening is that the pressure in this gap here will decrease, causing the outside pressure to push inwards and causing these two sheets of paper to close this gap. What would end up happening is these two sheets of paper will stick to each other, and the reason behind that is because the pressure in the middle is lower and the pressure to the sides is higher. It's not necessarily higher, it's just normal, but the pressure in the middle has went down due to the increase in velocity. So again, Bernoulli's principle relates the velocity, the pressure, and the height of a moving fluid. Now, let's go deeper into it. Now, instead of relating the pressure and velocity for one scenario, what we can also do is, if we look at a pipe, an inclined pipe that looks like this, and we have 2 points, point 1 and point 2. Let's call this the surface, and the pipe is inclined. This here is your elevation 1, Z1, and this is elevation 2, Z2. We're going to assume these points to be very small molecules of fluid. Each molecule has a different velocity, V1 and V2, and a different pressure, P1 and P2. Now, Bernoulli's equation also states that the total energy at this point must be equal to the total energy at that point. And the reason behind that is because the conservation of energy. Or another example is the continuity equation, which is the conservation of mass, which also states that mass at point 1 must equal to the mass at point 2. Which can also mean that the mass flow rate at point 1 equals to the mass flow rate at point 2. And since we know that this density equals mass flow rate over volumetric flow rate, we can then say that mass flow rate equals density times volumetric flow rate. Therefore, density times volumetric flow rate 1 equals density times volumetric flow rate 2. And since we're working with a compressible fluid, meaning that the density does not change, therefore the density can cancel, and the volumetric flow rate at point 1 equals to the volumetric flow rate at point 2. So again, the total energy at point 1 is equal to the total energy at point 2. Now, knowing that, we can use the known parameters at one point to find one unknown parameter at the second point. Okay, so if we know, for example, elevation of point 2, this is 2, and the velocity and the pressure is unknown, what we can do is we can use these parameters using the continuity equation or Bernoulli's equation. We can find P1. Now, Bernoulli's equation has 3 forms. It has an energy form, a pressure form, and a head form, which basically means the same thing, that instead of the energy at this point is the total energy at this point equal to the total energy at that point, it also means that the total pressure at point 1 is equal to the total pressure at point 2, and it also means that the total head at point 1 equals to the total head at point 2, and I'll list the equations below. So this is the first form of Bernoulli's equation, the energy form, which basically shows this here is the flow of energy. The first term is the flow of energy. Second term is the kinetic energy. And the third term is the potential. Energy. Okay, now all these 3 terms put together at one point equals the total energy, which also equals the total energy at point 2. So, and that's the reason it's a constant. So this term, this equation for point 1 equals this equation for point 2. So the only difference is going to be P1, V1, and Z1, and P2, velocity 2, and elevation 2, and so on. So that's the first form, which states that the energy at point 1 is equal to the energy at point 2. The second form is the pressure form, which states that the total pressure at point 1 must equal to the total pressure at point 2. Now, the total pressure is made out of 3 terms in each point. The first term is the static pressure, which, if you remember from the earlier chapters, was P equals gamma H. That's the static pressure when the fluid is not moving. Okay. The second term is the dynamic pressure, and the third is hydrostatic. Pressure. All these 3 terms together will create the total pressure, which is a constant on both points. So the total pressure at point 1 will equal to the total pressure at point 2. So the only difference, so this equation for point 1, where P1, velocity 1, and Z1 will equal to this equation at point 2, where P2 and velocity 2 and elevation 2. Okay, makes sense. Now the third form of Bernoulli's equation is the head form, which is the most common form. It's also made out of 3 terms. The first term is the pressure head. Second term is the velocity head. And the third term is the elevation head. Altogether, that will give you the total head. And again, it's a constant. So the same total head at point 1 will equal to the same total head at point 2. Therefore, the only difference will be at point 1 is P1, V1, and Z1 will equal to P2, velocity 2, and elevation 2. Okay, and then you can find the unknown. So that's it for Bernoulli's principle. It relates pressure, velocity, and elevation in one point. It also relates the pressure, velocity, and elevation from at point 1 and point 2, which the total pressure at point 1 and point 2 is the same, the total energy at point 1 and point 2 is the same, and the total head at point 1 and point 2 is the same. And the reason behind that is because the equation of continuity, the conservation of mass, which basically says that mass at point 1 is equal to mass at point 2. Therefore, the mass flow rate at point 1 will equal to the mass flow rate at point 2. And since we're working with incompressible fluids in this course, the density stays the same. It does not change throughout. Therefore, we can cancel the densities, and the volumetric flow rate is also the same from point 1 to point 2. So that was Bernoulli's equation. See you in next class.